All right, so my talk is, or my research has been on securing data on compromised hardware. So over the past number of years, probably past decade, we've seen an increase in the number of hardware attacks to the point that really, hardware attacks have vastly outpaced the defenses against them. So really the conventional wisdom that you hear repeated everywhere is that if an attacker has physical resource to your computer and some kind of reasonable resources, they're a clever individual, they have all of your data, whether it's encrypted or whatever or not. And some examples of this, the NSA has multiple hardware backdoors. Cold boot attacks can steal things out of your memory, including encryption keys. And my motivation for my research is really to look more closely at these claims and try to secure data on a machine that may be physically compromised. So there's a number of components to hardware trust. Specifically, when you're thinking about like mobile computing, so you have your laptop, there's a lot of cases where you can do via FireWire or Thunderbolt, you can do direct memory access. The device can directly read, potentially change your memory. You could have some kind of malicious device, changing your bootloader or your kernel to dump whatever, do literally whatever they want. And they could potentially even put some kind of backdoor in your case, as we've seen the NSA has the capability to do. It gets even worse for for like a desktop machine, because you're not going to open up your case and check for some hardware you don't recognize every time you turn it on. And it's very easy to slide something in the case. You don't even have to unscrew the computer. Yeah, and you even have to think about cold boot attacks, where someone can, as I mentioned, someone can turn off your computer and dump your memory because the DRAM does not lose its charge except for a few seconds later, and that's potentially a window where you could lose your encryption keys. So my goals for this research is to make it possible to have essentially as much security as possible. So I start with a simplifying assumption that I'll come back to kind of towards the end. But we assume that we have some kind of window during boot, during which we can trust the path from the kernel and bootloader storage device and potentially your keyboard for passphrase entry to the CPU. So we trust, at least initially, that we're able to boot securely. We have secure boot and these kinds of technologies enabled. After this window, we assume that the attacker has complete control over all of our hardware except the CPU, and we try to defend ourselves as much as possible against any kind of data stealing that they might do. So in order to talk about this, I defined this threat model, this data security hierarchy. And you can see on this triangle, we start at the bottom with both the largest and the most victimized, the easiest to attack data security or data storage mechanism. So this is your disk. Anyone can unplug your disk and plug it into any computer and read all the data that's there. It's completely non-volatile. Memory is a bit harder to attack, but really not by that much, because as it turns out, cold boot and DMA attacks, memory in reality is somewhere between non-volatile and volatile memory. It's not actually completely volatile, as we would hope. But then we get more onto the CPU die, and the story changes a lot. So CPU cache, CPU registers, there's really no way for a physical attacker to get access to these unless they're running software on your machine. And even if they're running software on their machine, they can't read arbitrary CPU registers for other applications unless they're in kernel mode. So really the idea behind my research is to try to move our TCB, our trusted computing base, as much as possible into the cache and CPU registers, and then try to use some kind of key storage in those devices to encrypt and secure disk and main memory against an attacker who could potentially read and maybe even write these. So I started by doing a lot of analysis and a lot of research into kind of the current state of disk encryption and where it is today. So your basic disk encryption that most people use on their laptops, if you just click encrypt my hard drive in Windows or Mac or even Linux, it's not going to be protected against any kind of cold boot or DMA attacks. So anyone who can gain access to your memory while the computer is running and the disk is unlocked has your encryption keys, and you're completely hosed. There's several ways to do this. As I mentioned, there's been a lot of research into various types of DMA, including things where someone literally just walks up to your computer while it's running, plugs in a little Thunderbolt device, and a few minutes later they have your encryption keys. So there was some research in 2011 entitled Treszura. It stands for Treszura runs encryption securely outside of RAM. So in this model, you can see in our little data security hierarchy thing, we've moved the trusted base where we store our keys up from memory into CPU registers, so that's our little red dot there. And the disk, we use that trusted storage to encrypt the disk, so we know that an attacker theoretically can't get access to anything that's on disk. And what Treszura does is it uses the CPU registers, so specifically it takes your debug registers away from you, and as it turns out, you really don't notice. The hardware breakpoint stuff is largely unused. Even a thing like GDB, it's like a 3-line patch to disable their use because there's already support for using non-hardware breakpoints. So beautifully, CPU registers, they're cleared on reboot and sleep. Sadly, this means we have to extend this trusted boot phase that I mentioned earlier into resume from sleep as well. So we have to trust that we can securely enter our passphrase from the keyboard directly into the kernel on resume from sleep. Sadly, Treszura, like all good academic research, is theoretical, and although there's an implementation, it's not particularly practical for daily use. It's really just a simple key derivation from a single passphrase you enter on your keyboard. If someone stands behind you and watches you enter your passphrase, you're completely hosed. Not just that, but humans are terrible at passphrase generation. We know that entropy of passphrases is just horrendous. Sadly, Treszura is not so ideal on its own. As it turns out, thanks to DMA attacks, a malicious device, there's a paper called Treszura Hunt a year later, a malicious device can potentially rewrite your kernel as your system is running to do whatever it wants, including dump the Treszura encryption keys that are so securely stored, dump them to memory, and then read them out. So we have to extend our little data security trust area to main memory again for at least the standard Treszura. So a lot of my research, at least for the first year, for the first 6 months, focused on doing a lot of research into DMA attacks, which ones currently work, how to protect against them, and various vulnerabilities thereof. So I end up with a lot of legwork to force the user to enable certain features. One of the most important ones is the so-called IOMMU unit that is in last few generations of processors. Specifically, you can think of it very similar to what the virtual address translation is. When you have a virtual memory address that a program accesses, it first hits a page table, which then translates it into a different address for physical memory access. Turns out there's a similar technology now for device accesses, which are doing direct memory access. So there's a pseudo page table that the DMA controller is going to access and check that both you're allowed to access the given range and that, and then also translate it into a potentially different physical address. So this is one of the main things that needs to be enabled to make Treszura actually secure. It's not the only one. There's a number of other things discussed in the paper, but I won't really get into it right now. As I mentioned, Treszura is really kind of an academic thing, and it's not particularly practical. It only uses passphrases, and one of the most important things that a lot of commercial disk encryption solutions are going to give you is support for key files. For simplicity of implementation, I decided against using key files and used a different term called key sectors, which is to say a specific sector on your device is used as the additional input into your key derivation function. So this provides a reduction of your single path of trust. Instead of having to trust your keyboard to your CPU, you can now trust both the keyboard and some other USB controller if you have it on a flash drive or some other device. However, key devices can be largely brute forced, so if someone gets your passphrase and the device itself, without needing to necessarily know where on the device it is, they can just guess all of the sectors because really there's not that many sectors on a drive, at least when you're talking about an offline attack or brute forcing something. So what we do instead is we come up with custom hardware, this being one of them. It looks like a normal flash drive, but in reality, it's an encrypted SD card that has a bunch of hardware to prevent someone from brute forcing or reading the majority of the device. So what happens is you encrypt the SD card, and if the device detects that you read to any one of a number of very large sections of the device which are considered illegal access, in fact the majority of the device by far is considered illegal access, it will press the big red button and destroy itself. So you won't be able to get the encryption keys off of it without knowing the correct passphrase to give the device itself. So I'm going to take a quick detour now that we've at least set up a secure Treszura key storage device for our encryption, disk encryption. I'm going to talk about shared machines. So one of the things I worked on in my research was to think about how a user might trust a remote system to store given data. And in this case, you really don't want to trust one system administrator who has your drive encryption keys for all of your data. So ideally, you'd like to be able to trust some quorum of system administrators who all together control the drive encryption keys, and then also trust that the system is secure against physical attack. So note that we require all of the previous work with Treszura to get to this stage, but on top of that, I implemented some simple Shamir secret sharing where multiple system administrators are required to enter key sectors before a drive can decrypt. Okay, so that's all on disk encryption, but as I mentioned, we don't want to just encrypt the disk. We also would like to encrypt as much of main memory as possible. So obviously, x86 doesn't allow for this yet, but with a ton of rewriting the kernel code, I have like 5 more slides, but okay. With a ton of rewriting the virtual memory system in Linux, which is really freaking hard, by the way, you can encrypt large sections of memory and then use page faults to actually decrypt the memory as you go when it's accessed by applications. And it turns out you can do this with with reasonable performance overhead. I won't say little to none. The top line is the total runtime for a program that just simply scans through memory sequentially in an attempt to constantly trigger page encryption and decryption. And the bottom line is that same program's system time, so the amount of time actually spent decrypting pages. And finally, we get beautifully, disk is encrypted and memory is mostly encrypted. Hopefully you hit your secrets, and then CPU registers are used for actual key storage. Not really.